we are told if f of x is equal to x to the power of 46 plus x to the power of 45 plus 2, all over 1 plus x, calculate the 46th derivative of f of x, where x is equal to 3. So that's what this notation right here means. It means you take the 46th derivative of this expression, and they want you to find the value where you plug in 3 for x. And then they say express your answer in factorial notation. And a review of what factorial notation is when you have a whole number with an exclamation mark beside it. That's called your number factorial. So for example, 7 factorial is the product of all the numbers from 1 to 7. So that would be 1 times 2 times 3 times 4 times 5 times 6 times 7. 17 factorial would be 1 times 2 times 3 times 4, all the way to times 15 times 16 times 17. And we'll get to this factorial part later, you'll see why it comes in handy. But our main goal here is to find the 46th derivative of this expression. Now to clarify what 46th derivative even means, when we take the derivative of f of x for the first time, that's called the first derivative. If we take the derivative of the first derivative, that becomes your second derivative. If we differentiate the second derivative, that becomes our third derivative. And if we keep going like this 46 times, we will arrive at our 46th derivative of f of x. So essentially, if we take our d over dx of our 45th derivative of f of x, we will get our 46th derivative of f of x. And the reason we put this number up here is, well, we usually put our tick marks, right? This is our first derivative, and this is our second derivative. But once we get to really high order derivatives, it makes much more sense to put a number here than 46 of these tick marks. So that's what the 46th derivative means. So how do we actually find it? Are we meant to take this expression and actually differentiate it 46 times? No, there's actually a more efficient way to do this. When you get these questions with these super high order derivatives, the idea is to take the derivative a couple of times and then see what pattern you get. If you can find a pattern for the nth derivative, meaning you know what derivative number you're on and you can find the expression given that number, then you're good to go. You can find the 46th derivative. But as I said, we have to calculate the derivative a few times first. So let's try that. Let's try to find our pattern by taking the derivative a few times first. So f of x is x to the power of 46 plus x to the power of 45 plus 2, all over 1 plus x. Or I can also write 1 plus x as x plus 1. Okay. Now, you may realize that the only way to differentiate f of x is to use the quotient rule. And a reminder of what the quotient rule is, when we have d over dx of some fraction where we have an expression with x in the numerator and an expression with x in the denominator, the derivative of this expression with respect to x becomes another fraction where we have g of x squared in the denominator, so g of x squared, f prime of x times g of x minus f of x times g prime of x, all in the numerator. Now you may realize that if we take the derivative once, this expression will already get pretty messy. Imagine we'll have to use the power rule first of all for our f prime, which is our numerator. And by the way, this f of x is not the same as this f of x. This is just a general f of x for your numerator. This is just to explain the quotient rule. But if you take the derivative of your numerator and subtract and multiply it by your denominator, subtract it by your numerator times the derivative of your denominator and square your denominator, that's already going to get very messy. And then you have to do it another time, and then another time. And the problem with that is, first of all, there's a lot of algebra involved, and second of all, you may not see the pattern. So that's an indication that there might be some way to simplify f of x. And one way I see that we can do it is that we can factor out an x to the 45 from these first two terms. And that's going to help us because then we'll get an x plus 1, and that can cancel with the denominator. So just to show you what I mean, we have x to the 45 factored out from these first two terms, and that becomes x plus 1 in brackets. We still have our plus 2 on the outside, and we have an x plus 1 in the denominator. Now, if we divide both terms by x plus 1 here, we get a much more simplified f of x. So this gives us f of x is equal to x to the 45 plus 2. I could write this as 2 over x plus 1, but since we're going to differentiate it, it may be easier to write it as 2 times x plus 1 to the power, I'll clean up my bracket, x to the power of negative 1. X plus 1 to the power of negative 1. Now, the reason this is easier now is that we have two terms here, just two terms. And we know that the derivative of the sum of two terms is the derivative of the first term plus the derivative of the second term. So this means that if I'm taking, this is the notation for the nth derivative, n is some whole number, like your first derivative, second derivative, third derivative, etc. If I'm taking the nth derivative of f of x, this means that I'm taking the nth derivative of my first term here, x to the 45, and I'm adding that to my nth derivative of my second term. And one note, I can also take the constant out here so that we can just think about the thing we actually need to differentiate. We can take your constant 2 and put it out here. So we're taking 2 times the nth derivative of x plus 1 all to the power of negative 1. Okay, so here's what we're going to do. I'm going to take the derivative of this a few times and try to find the pattern for x to the 45. And then I'm going to do the same thing with x plus 1 to the power of negative 1. And once we find a pattern for both of these, a pattern where if we know what derivative number we're on, we can find the actual derivative. Once we find that, we're going to find the 46th derivative for x to the 45, the 46th derivative for x plus 1 to the power of negative 1, and then put it back into this equation. We're going to find the 46th derivative and put it here for x to the power of 45, find the 46th derivative of x plus 1 to the power of negative 1, and then multiply it by 2, and then we'll see what we get. We'll get an expression with x in it. And once we do that, that will be our 46th derivative of f of x. And then the final step will be to plug in 3. So that is the plan. So let's start with our finding a pattern for x to the 45. So let's say y is equal to x to the power of 45. So if I differentiate this one time, I can say that dy over dx is equal to, I'm going to put my constant in red out here. So we're using the power rule. And the power rule tells us that we bring down the exponent and we decrement the exponent by 1. So 45 minus 1 is 44. If I take the second derivative, this becomes d squared y over dx squared. And we just take the derivative of this. So that means we keep our 45 out front, and multiply it by this, 44, this exponent, 44. And then we decrement the exponent of our x. So this becomes x to the 43. Let's take the derivative one more time for good measure. We can sort of see the pattern forming already though. So d to the 3 y over dx to the 3. This becomes, well, we're going to keep our 45 and 44 out here. So 45 times 44. And now we're going to bring down this exponent, 43. And then we're going to make it times x to the 43 minus 1, which is 42. Now we can sort of see the pattern forming here. We can see that each time we take the derivative, we're subtracting 1 from the exponent. And each time we take the derivative, for the first derivative, we're starting with times 45. And then for the second derivative, it's times 44 times 45. So it's 45 times the number 1 less than 45. And then we're multiplying by the number 1 less than 44. Now, can we come up with a general rule for this? Can we come up with a general rule for if we have d n y over dx to the n, can we come up with a general rule? So we know that each derivative here has some constant in front of it. So I'll call this constant c for now, some arbitrary constant, and we'll worry about it later. But let's think about the exponent on x. So we know that the exponent for x starts at 45. And for each derivative, the exponent decrements by 1. This is the pattern that we found. And let's check if this works. So for the first derivative, the exponent should be 45 minus 1, because n is equal to 1 for our first derivative. So that is indeed true. Our exponent is 44. And what about for our second derivative? 45 minus 2 should be our exponent, and the exponent is indeed 43. For our third derivative, it should be 42, because our exponent should be 45 minus 3, and so on for the nth derivative. So that's pretty good. We've got a general rule for our nth derivative now. But now this is the key realization. What happens when I take my 45th derivative? We know that our 46th derivative is the derivative of our 45th derivative. So it's very important to know what our 45th derivative is. Let me write that down. So we know that d over dx of our 45th derivative, here I'll write it in this form. We know that d over dx of d45 y over dx to the 45, we know that this is equal to d to the 46 y over dx to the 45. This is our 46th derivative, so this is what we're looking for. Now let's think about our 45th derivative. So when we're taking our 45th derivative, we have to plug in 45 for n, and this means that the exponent on our x becomes 45 minus 45. The exponent, if I copy and paste this, we're trying to find the 45th derivative of x to the 45. We know that the exponent becomes x to the 40. We know that our exponent becomes x to the 45 minus 45, which is x to the 0. So really, which is 1, which really means our 45th derivative is some constant. And what happens if we take the derivative of some constant? The derivative of some constant is always 0. So therefore, the 46th derivative of x to the 45 is 0. This rule cannot work for x to the 46. You may be wondering, why don't we just plug in 46 here? Well, that's because the 46th derivative is defined as the derivative of the 45th derivative. We can't just use this rule blindly if we're not following this rule right here. So since we know that the 45th derivative is a constant, because the exponent on x is 0, we know that the 46th derivative must be 0. So what does that mean? We can plug in 0 for this term right here. And now we think about this term. Now we're going to follow a similar exercise for x plus 1 to the power of negative 1. So let's do that. Let's do it on this side here. Let's say that y is equal to x plus 1 to the power of negative 1. This means that dy dx is equal to negative 1 times x plus 1 to the power of negative 2. So I just used my power rule there. And notice that if I use chain rule as well, if I take the derivative of the inside, well, the derivative of the inside is just 1. So I don't really have to worry about the derivative of the inside. It doesn't impact my derivative all that much. Now, if I take the second derivative, my second derivative becomes, I'm going to keep my negative 1 in the front here, and I'm going to multiply it by this exponent, so negative 2. And I'll decrement to the exponent on my x plus 1, so this becomes x plus 1 to the power of negative 3. And let's do it one more time for good measure. We can sort of see the pattern forming here. One thing I want you to notice is that when n is equal to 1, our constant out here is negative. But when n is equal to 2, our constant out here is negative times negative, which is positive. So we can sort of see that the constant sort of switches between positive and negative. So we'll have to account for that in our nth derivative rule. So the third derivative of x plus 1 to the power of negative 1 is equal to negative 1 times negative 2 times this exponent, negative 3, times x plus 1 to the power of negative 4. I just decremented this exponent. Okay, now let's try to find our general pattern for this. So we are trying to find dny over dx to the n. So let's first think about how we're going to account for the slipping between negative and positive. Notice, if we take the fourth derivative, this will become negative 1 times negative 2 times negative 3 times negative 4, the constant out here. So for our fourth derivative, our constant will indeed be positive. So we can sort of see the pattern, how when our derivative number is even, the constant is positive. If the derivative number is odd, we can see for the first and third derivative that the constant is negative. So how do we account for that? Well, we would account for that by putting a negative 1 in our expression for our nth derivative and putting n in the exponent for 1. Now the question is, do we make our exponent n or n plus 1? Well, let's try n first and just check if it works. Well, when n is equal to 1, our constant is indeed negative. If n is equal to 2 for our second derivative, negative 1 squared is indeed positive, and our constant is indeed positive. So we know that this works. When n is odd, our constant will be negative, and when n is even, our constant will be positive. If it was the other way around, you would just add an n plus 1. Okay, now we have to think about our actual constant, the absolute value of our constant. Now, this is where our factorial notation comes in handy. We can see, now we're just thinking about absolute values, remember that. Just ignore all the negatives. In your mind, ignore all the negatives. So we can sort of see that when we're on our first derivative, we just have 1. On our second derivative, we have 1 times 2. Well, 1 times 2 is really the same thing as 2 factorial. This is the same thing as 2 factorial. And this is the same thing as 3 factorial, because we have 1 times 2 times 3. And we can see that for our fourth derivative, we'll have 1 times 2 times 3 times 4, which is 4 factorial. So we can see that the derivative number lines up with the factorial. So that means we can write that the absolute value of our constant out here is going to be n factorial. Let me put this in brackets so it's a little neater. N factorial. Remember, all n factorial means is the product of all the numbers from 1 to our number n, if we remember our definition of a factorial here. Okay, now we have to think about the exponent of our x plus 1. We know that in each derivative we have an x plus 1, so we can just put an x plus 1 in here. So x plus 1, and what is its exponent going to be? Well, we know that the exponent starts at negative 1, so we can put a negative 1 in here. And another thing we know is that similarly to x to the 45, we are decrementing the exponent by 1 each time we take the derivative. So this means we can say that the exponent is negative 1 minus n. And does this work? Well, if n is 2, if we're on the second derivative, the exponent should be negative 1 minus 2, which is negative 3. And for the second derivative, we are indeed on x plus 1 to the negative 3. So this is our rule for the nth derivative. And notice, this rule will actually work for the 46th derivative, unlike our other terms' nth derivative rule. And that's because, well, it works for the 45th derivative as well, right? There's no positive number for n where we can get a constant here. Well, we will always have an x plus 1 in our expression. So let's do that then. Let's find our 46th derivative. So we are finding d46y all over dx to the 46. And we're just plugging in the number 46 now. This becomes negative 1 to the power of 46. Now if we have negative 1 to an even power, that's just 1. So we don't have to write this over here. But we do have to write 46 factorial. 46 is our n, so we're going to write 46 factorial. And then what's our exponent? Well, our exponent is going to be negative 1 minus 46, which is negative 47. So our exponent is negative 47. And that's it. That's our 46th derivative of, can't forget, of this term. So we found the 46th derivative of this term, and let's write down what that is. Actually, let me copy and paste this entire thing here so I have some room. So copy, and paste. So we got from our little exercise over here that the derivative of x to the 46th derivative of x to the 45 is just 0. And we got from over here that the 46th derivative of x plus 1 to the power of -1 is 46 factorial times x plus 1 to the power of -47. All right. And what does this mean? This means that we have our 46th derivative for this entire expression. We have the 46th derivative of the first term and the 46th derivative of the second term. We just have to take this and multiply it by 2. Let's write out what our 46th derivative is. Let's clean this up a little. So our 46th derivative with respect to x, notice that I'm using the prime notation here, is 2 times 46 factorial, and I can write this in the denominator, all over x plus 1 to the power of 47. And our goal here, right, was to find the 46th derivative and just plug in x equals 3. Let's do that. So we're finding the 46th derivative where x is equal to 3. And this becomes, we deserve a little drum roll here, 3 plus 1 is 4, so we have 3 plus 1 to the power of 47 in the denominator. So we have 4 to the power of 47 in the denominator. And our answer is the 46th derivative of f of x, where x is equal to 3, is 2 times 46 factorial all over 4 to the power of 47.